Swayam Prabha. Digital India. Educated India.
So, we continue with our discussion on inter-process communication. If you recall, in our last lecture, we discussed some of the possible solutions that we can use to solve the critical section problem among a number of cooperating processes. We discussed a solution based on disabling interrupts, some software solutions, and also some solutions based on hardware instructions and mutex lock. In this lecture, we shall first be talking about something called semaphores, which is a very general synchronization tool, not necessarily used only for mutual exclusion, only for solving the critical section problem, but there are other utilities as well. Okay. So, first let us see what is a semaphore and how we can use semaphore for synchronizing processes in various different ways. Let us see. First, let us try to define a semaphore. Firstly is that a semaphore is a synchronization tool. Let us appreciate that first. Semaphore, say technically speaking, semaphore is a variable, but basically it is a tool which you use for synchronization. So, in that sense, you can say a semaphore is nothing but some synchronization tool that can be used by processes to coordinate and synchronize their activities. Now, you may argue that well, we have already seen some methods like mutex locks in the earlier lecture, but the issue is that semaphores are much more general than the mutex locks that we have seen earlier, because mutex locks can only be used for locking and unlocking, nothing else. But here we will see that is semaphore. There are a few other facilities which you can use that can be more general. Now, the first thing is that what is a semaphore? Technically speaking, as I said, a semaphore is essentially an integer variable. Not only that, in the definition of a semaphore, there are three things you have to specify. First is that it is a integer variable, and second and third are there are two operations that are defined on that variable. These two operations are called wait and signal. So, if anyone asks you what is a semaphore, your answer will be semaphore is a variable, integer variable on which two atomic operations wait and signal are defined. These two operations must be atomic. It is not like any function you are writing in C, because when you write some function in C, that is not atomic. If an interrupt comes, there can be a context switch, there can be preemption. But when I say this wait function is atomic, it will mean if some process calls wait, either this wait will execute completely or it will not execute. It is not that it will execute halfway through, it will execute while and after that it will get preempted. There will be a context switch, not like that. So, let us see what is the essential idea in this solution. First thing is that I said S is an integer variable, it can hold integer values. So, the convention that you are following is that the value of S, if it is negative, our convention says that if the value of the semaphore variable is negative, it means that the resource that we are considering is locked. That means we have locked something. But if the value of S is positive, greater than 0, then it is unlocked. So, let us look at the functions, what these functions say. First is a wait function which operates on the semaphore S, semaphore variable S. It checks whether the value of the semaphore is less than or equal to 0. If it is 0 or negative, which means it is locked. So, So, it is not necessarily S is negative, it can be 0 as well. If it is either 0 or negative, it is locked. So, a process when it is calling wait, this function will be checking whether S is 0 or negative. If it is 0 or negative, it will be waiting here. So, in this definition, there is a busy waiting. But if it finds that S was greater than 0, 1, 2, 3, whatever, that means it was not locked. What it will do? It will simply decrement S by 1. S minus minus means S equal to S minus 1. This is nothing but S equal to S minus 1. In contrast, the function signal is very simple. It simply increases the value of S by 1. S plus plus means S equal to S plus 1. So, basically speaking, the function wait decreases the value of S by 1 and signal increases the value of S by 1, but in wait, before you are decreasing, you are checking whether it is already 0 or negative. If it is so, then you do not decrease, you wait. As soon as it becomes positive again, only then you decrease. Okay? Now, using semaphore, what you can do, let us see now one by one. The first thing is that we look at the solution to the critical section problem first using semaphore. Here, the assumption we are making is that the semaphore, see here you are declaring a semaphore S with an initial value of 1. So, this semaphore value S that we are considering in this problem, solving the critical section problem, we are assuming that this is a binary valued variable, it is a boolean. The value can be either 0 or it can be 1. The convention we are following is that 0 means, this is the convention we are following, 0 means locked and 1 means unlocked. So, that is why initially the value of S is set to 1, which is unlocked. Now, the solution in terms of the processes are very simple. So, we declare a semaphore S which we are using to protect the critical section among a number of processes. Let us say 2 processes P1 and P2. So, before entering the critical section, in the entry code, the process calls wait of S. In the exit section, it does signal of S. P2 does the same thing. Let us see what happens here. Suppose initially the value of S was 1, right? S was initialized to 1 initially. Now, when P1 does a wait S, what will happen here? If you look at the definition of S, it will first check whether S is 0 or negative. No, it is not, S is 1. So, it will decrease S by 1. So, S will become 0 and it will enter the critical section now. Suppose in the same time P2 was trying to enter the critical section. So, P2 will again come in here, P2 will again try to do a S, wait S. But what P2 will see now, so while trying to do wait S, it will see that well my value of the semaphore variable S is 0. So, it will wait in that while loop, it will not be able to enter the critical section. So, it will be waiting here. So, how long it will wait? See, P1 is inside the critical section, P1 will finish it, it will come out, it will come to the signal S, signal S will increase the S by 1, it will make the value of S again equal to 1. Now, as soon as it makes S equal to 1, the other process which was waiting will now see that S has become 1. So, in the while loop it will now come out. and then it will make S 0 again. So, like this it happens, and this will work correctly for any number of processes. This is not necessarily true for 2 processes, it can happen for any number of processes. So, for semaphore, the 2 functions which are defined are called wait and signal, but traditionally this wait and signal were also referred to as the P operation and V operation. These are Dutch terms, but anyway, now we refer to them as wait and signal. Let us follow that. Okay. Now, there are some other applications of semaphore as well. Let us look at a scenario like this. There are 2 processes which are running. There is a process P1, there is a process P2. So, P1 contains a number of statements, P2 contains a number of statements. Now, it may so happen that inside P1, let us say there was a statement called S1, and inside P2 there was somewhere a statement S2. Now, there can be some kind of a dependency, like you may say that, well, I have written the program in such a way that S2 can execute only after S1 has finished, which means there is a dependency like this. Unless S1 finishes, the process P2 after reaching S2 will have to wait. Only after S1 completes, P2 can continue and execute S2. So, for this kind of a process synchronization problem, we can also use a semaphore, but here the convention we are following is slightly different. We are declaring a semaphore, let us call the name as sync, but now in the earlier case we are initializing the semaphore variable to 1, but now we are initializing it to 0. That means by default the semaphore is locked. Okay. Suppose P2 was executing first. So, P2 executed all the statements that were before, and just before S2 I have inserted a wait statement. So, it will come to wait, it will check that the value of sync is 0. So, in that while loop it will wait, it will not continue to S2. So, how long it will wait? You see, the process P1, it will execute these statements, it will also execute S1. After that, we have inserted a signal statement. So, the signal statement will make the value of the variable sync to 1. This will indicate that S1 has finished. After S1 I have inserted a signal. So, as soon as this is done, this wait will come out of that while loop and it will allow, and this the value of sync will again become equal to 0 and it will allow it to continue to statement S2. So, this kind of a synchronization can be done for any number of processes any number of times, but just remember one thing, for one such synchronization S1 to S2 you need one semaphore variable. Suppose there is one more synchronization between here and let us say some other place, so you may need another synchronization variable for that, right. So, it depends on the application. So, semaphores can be used for mutual exclusion, for process synchronization, 2 of the applications we have seen. And the other thing is that depending on the possible values a semaphore can have, the 2 examples that we took so far, there the values of the semaphore can be either 0 or 1, they are binary valued. Okay. Never the value of semaphore could be greater than 1, just think, can be either 0 or 1. So, depending upon the possible values a semaphore can have, we can either classify it as a binary semaphore or as a counting semaphore. Now, counting semaphore is sometimes also referred to as a general semaphore. Now, binary semaphore means it can be having a value 0 or 1. So, essentially this is very similar to mutex lock as we have seen earlier. Okay. Now, this binary semaphore we have already seen two applications. So, one application was mutual exclusion to solve the mutual exclusion problem, and the other application was solving some process synchronization problem. So, some statement S1 must execute, only then S2 can continue. Now, a counting semaphore is a more general kind of a definition where the semaphore value can range over any integer values. In general, it can be negative, it can be positive, it can be 1, 2, 3, minus 1, minus 2, minus 3. And we shall see later with some examples, so I am not showing the examples now, that this counting semaphores can be used for a third kind of application which is referred to as resource counting. Like for example, let us say you are reading some data values, some kind of data, and you are storing them in a buffer. You want to keep track of how many data values I have stored in the buffer. That you can define a counting semaphore, and every time you store an item in a buffer, you can call signal with that semaphore name, the value will increase by 1, 2, 3, 4. And once you take an item out of the buffer, you do a wait on that, it will decrease by 1. So, it keeps a count. Okay. So, broadly there are three applications: mutual exclusion, process synchronization, resource counting. For resource counting, you need a general or counting semaphore. Okay. Fine. Now, let us see, semaphore is a concept, is a definition, all right, but how do we implement semaphores? There are two different implementations we talk about. The first implementation of semaphore involves busy waiting. So, when I say we want to implement a semaphore, essentially we are saying how we are implementing the wait and the signal functions. So, the important thing is that how do we implement wait, how do we implement signal. The most important thing is that both these functions must be atomic, because unless they are atomic, you cannot ensure mutual exclusion or correctness of operation, right. So, you must ensure somehow that because of this atomic thing, that two processes, two or more processes must not execute wait or signal on the same semaphore at the same time. While one process is executing wait on S, another process at the same time cannot execute wait or signal on S, because they are atomic. While wait is working, no other process should be able to execute. So, the execution of this wait and signal must be mutually exclusive in time. Okay. So, basically what it means that you are trying to make wait and signal atomic. Basically, you are trying to solve the critical section problem with respect to wait and signal. They should not execute together. But if you simply make an implementation like this with the definition of wait and signal as we have seen earlier. So, in the wait definition, there was a while loop where you were waiting. If the value of semaphore was negative or 0, it was doing in a spin lock, it was doing busy waiting. So, in that implementation, there was busy waiting. Now, the thing is that if you want to make this wait and signal atomic, you can have a busy wait implementation in the critical section, and the critical section code will be very small because the wait and signal are only a few instructions. So, it will not take much time. The critical section will be occupied for a very short time, and most of the time you will find that the critical section will be empty, right. But if you look at the application, this is with respect to wait and signal, but if you look at the processes, at the process level the critical section can be many instructions. So, there is no restriction that the critical section code has to be very small. You may be doing lot of updates on the shared variables in the critical section. So, in general for applications inside the critical section you may be spending lot of times. So, again I am repeating what we are doing here. At the process level, which you are saying application, there we are ensuring mutual exclusion by inserting wait and signal. That is the tool we are having with us, semaphore. But at the lower level, when you are thinking about how this wait and signal are implemented, they are implemented using those while loop, s plus plus plus, s minus minus that we have seen. But inside that there is again a small critical section problem coming in, because wait and signal, they are both updating a common shared variable, the semaphore. So, that has to be protected as well. So, there is a second level of a critical section problem coming in with a very short critical section there, s plus plus or s minus minus, that is the only part. Okay? This is what I am trying to say. Fine. Now, let us look at a more general implementation. General means we are saying that we want to have a semaphore implementation where we do not want to waste CPU time, no busy waiting. So, what do we want to do then? Suppose a process was executing, let us say a process was executing and somewhere it executed a wait on a semaphore. Let us say the initial value of semaphore s was 0. So, as per the definition, the process is supposed to wait here. Now, in our earlier solution we said that the process was waiting by a spin lock in the while loop, it was wasting CPU time. But what better can you do? If you think, you can say that well, a process had called a wait call, but because the semaphore was 0, it was not able to proceed. So, why do not you put this process in the block state? In the current scenario, the process cannot continue in the running state, move it to the block state. If you move it to the block state, it will not occupy CPU time anymore. It can wake up when an event occurs. What is that event? That event will be whenever the value of s becomes greater than 0, that is the event. So, whenever someone executes a signal on a semaphore, automatically you check whether there was any process which was waiting on that semaphore. If so, wake up that process, move from the block state to the ready state again. This is how we are thinking about the solution here essentially. Okay. So, you see, with every semaphore we are associating a queue. This is referred to as the waiting queue. So, what does this waiting queue indicate? This waiting queue is basically a queue of the processes. Waiting queue is nothing but it is a queue of processes waiting on the semaphore. There can be multiple processes who have done a wait, but the semaphore is currently locked, it cannot continue. Now, in the queue, what does the queue contain? The queue basically contains, let us say for a semaphore S, it contains the value of S and a pointer. Pointer means the address of something. Now, what it does? It will contain a pointer of a number of processes, let us say P1, P6, last pointer will be pointing to null, this is null. Essentially what it says is that this queue will contain the value of the semaphore, it can be 0, 1, 2, 3 whatever, and it will contain a linked list of all processes which are waiting on that semaphore. We are maintaining a list like that. So, as I said, this total queue that we are talking about, it contains essentially two information. One is the value of the semaphore, this S, and a pointer to the next element of the list. It is actually a linked list. You are pointing to the first element in the list and the last element is pointing to null. Okay. This is the data structure we are maintaining additionally in this implementation. Let us see what else we are doing. So, we are also defining two additional system calls. One system call is a blocked, well, you again recall that process state transition diagram, I am just showing it again. You have a ready state, you have a running state, you have a block state. So, from ready to running you can go either way, you can go from ready to running or running to ready. From running you can go to blocked, from blocked you can go to ready. Now, when a process, let us say a process P was running, in between there is a system called block, it calls block. So, the process was in the running state, if it calls the block function system call, then this transition will be forced. The process will be moving from the running into the block state. So, with respect to the semaphore, what it means is that the process will be added to the corresponding queue, corresponding waiting queue of the semaphore. So, if you recall earlier that there are multiple queues which are maintained for the processes in the PCBs, process control block. For all processes in the block state, there can be separate queues, one queue for every event. For semaphore, there can be one queue for every semaphore. Semaphore S1, one queue, semaphore S2, another queue, like that. Okay. Similarly, there is another function called wake up, where you can pass a parameter P as the parameter, P is a process ID, the ID of a process. So, when you call wake up, essentially you are activating this transition. You take that process away from the semaphore queue and the corresponding process you move it to the ready state. It was earlier blocked, now it is now again ready to execute. Okay. Now, with this you can very easily define a solution, or means the way the wait and signal functions can be implemented. Let us see. The first is that here this is essentially the structure definition of the queue. So, what I said, what was the structure definition? It consisted of two parts. One was a pointer, other was a value of the semaphore. So, the pointer definition we are calling as the list and the semaphore value we are calling as semval. So, you see this is a C like declaration, we are defining a structure. So, one element of the structure is an integer value which is semval, the value of the semaphore, that is the name of the variable you are giving, and then we declare a pointer called list which is pointing to a process structure process. So, actually from here it will be pointing to a process structure which will be chained in a linked list like this. and this whole structure definition we are defining a data type, we are calling it as semaphore. So, for every semaphore you are defining, there will be a semaphore value and there will be a list of waiting processes for that semaphore, right. Now, we refine the definitions of wait and signal. Earlier it was a very simple definition. In the wait definition, if you recall, we are simply checking while the value of s is less than or equal to 0, just wait in a loop, come out, do s minus minus, and for signal it was simply s plus plus. But here it is slightly more involved. What we do? Look at the definition of the wait function. So, this is a C-like notation again we are using. Here we are saying that we are passing a parameter called s, which is a pointer. It is a pointer to s, that means address of s, and it is of type semaphore. So, this structure definition already I have said what is semaphore, that is the structure definition. Now, what I do in that, see here, see earlier what it is in the original definition, first we do in the while loop, then we decrease s by 1, but here we do it in the other way around. We first decrease the value of semval by 1. Now, you recall this notation s arrow semval, this is a notation that is used in C or C++. This s indicates a pointer, it is pointing to something, and this indicates the name of the variable of that structure where it is pointing to. So, it is pointing to a structure. So, s was pointing to a structure of type semaphore and semval is one component of the structure. So, what it is doing? It is decreasing, minus minus means it is decrementing semval by 1. Now, after decrementing it is checking that whether the value of semval has become negative. If it has become negative, then the process which has called wait, you put it to the block state. How do you do that? You do two things. First, you add it to the semaphore waiting queue, add the process to this S list, this list that I have shown here. Then you call the system call block, which will move the currently running process from running to blocked. So, now the process has blocked, some other process will get chance to run. Now, similarly you are defining signal, some other process may be, see in this way, suppose there are many processes which are means calling wait. Suppose the initial value of semval was 1, semval initially was 1, let us say. There are 3 processes, let us say, which is called wait. First time, the first process, it decreases semval by 1, semval becomes 0. But if it is not less than 0, not negative, so it will not block, it will enter the critical section. But for the other 2 processes, for the first one s will become minus 1, for the third one s will become minus 2. So, they will be waiting because now semval is less than 0 for them. So, the one process will be in the critical section, 2 processes will be waiting and they will be put in the list. Now, once the process which was in the critical section has completed and let us say it is now calling signal that I am done. So, what signal will do? First it will increase the value of semval by 1. See, semval currently was minus 2 in the example I have cited. Minus 2 means there are 2 processes which are waiting. So, if you increase the value of semval by 1, so now the value of semval will become minus 1. Now you check if the value of semval is less than or equal to 0. Less than or equal to 0 means semval was negative, after increasing it by 1 it is less than or equal to 0. What does that mean? It means that some process was already waiting for the semaphore. So, there was a chain of waiting processes, one of them take out and wake it up, because one of them can now come out of their wait and they can continue. So, in the example I have taken, two processes are waiting, right. So, what you do, remove one process from the corresponding queue, P list, S list. Let us say that process ID is P, and move that process into the ready state. So, now the process again becomes ready to run, but now there are two processes waiting, now there will be one process waiting, and this thing will continue. So, if you maintain this linked list, maybe your implementation will be a little more elaborate, but you are saving on CPU time quite significantly, right. So, you are not losing or wasting any time. So, whenever a process is in wait and has to really wait, it will move itself to the block state, it will not consume any CPU time. And whenever some other process executes signal, automatically there will be a check whether some processes were waiting. If they are waiting, one of the processes will be waking up and it will be moving to the ready state. Okay, fine. Now, the point to note is that when you are using semaphore, typically this wait and signal operation must occur in pairs. So, what do you mean by that? Let us say there are two processes P1 and P2. So, if you think of the critical section problem, before entering the critical section, you call wait, then you have the critical section here, after coming out you have signal. Same will be true for P2. So, before entering its critical section, it will be doing a wait, it will enter the critical section, it will come out. This is for mutual exclusion. Similarly, for process synchronization, we mentioned the same thing. There are two processes, let us say P1, P2. P1 executes a wait on some semaphore, let us say yes. P2 executes a signal, and this signal can wake up this particular process, it can continue after that. This is for process synchronization. But let us see here, what I am trying to say is that if this matching wait and signal are not there, by mistake instead of signal you have written wait, or instead of wait you have written signal, then the behavior of the processes will become wrong. Either two processes will be entering the critical section, or a process will be waiting indefinitely, something like that will happen. You take another scenario. Suppose there are two shared variables, two shared items, and you have defined two semaphores S1 and S2. Let us say there are two semaphores S1 and S2, both of them are initialized to 1, both of them are initially unlocked. Okay. Suppose inside the process you do this, there is some instruction, then you give wait S1, then you again give wait S2, that means you are wanting to update both S1 and S2, then you do both, update them, this will be your critical section, then you do signal S2, signal S1. Right. Now, say there is another process P2 which is doing something similar, they will also be updating the variables corresponding to S1 S2, but here instead of writing wait S1 and wait S2, suppose by mistake you wrote wait S2 first and then wait S1 and then critical section whatever signal after that. Now, here what might happen? Here you see it can so happen that the process P1 executes this wait S1. Okay. So, the value of S1 becomes 0. Here there is a context switch, after that there is a context switch. Now, P2 starts executing. So, P2 will be executing wait S2. Well, S2 is 1, sorry, S2 is 1. So, S2 will also become 0. Now, both S1 and S2 are 0. Now, you see what will happen. P1 will try to do wait S2, P2 will try to do wait S1, but both S1 and S2 values are 0. So, none of them will be able to do it. So, both P1 and P2 will be waiting for the other fellow. This is a scenario which is called deadlock. None of the two processes can proceed, both of them will be waiting indefinitely. So, when you are coding a program using wait and signal, you must be careful how you are using this wait and signal. If you are not careful enough, so such cases of deadlock may happen. So, apparently your code may look fine, but you have changed the order of this S1 and S2. So, it might lead to some inconsistent behavior. Okay? Fine. Now, the next thing that we discuss is something called monitor. Monitor is again a synchronization tool, but is at a slightly higher level. When you look at a high level language program, when you look at object oriented programs, there also you need to do lot of synchronization. There may be two functions or two procedures which are trying to access some common shared variables. So, monitor is a mechanism or a synchronization tool that is available in many high level languages. Okay, they give slightly different names, but generically it is called a monitor. There are some facilities available in Java, something in C++, etc. Let us see what a monitor is generally. First thing is that it is a high level synchronization tool. High level synchronization tool means typically you will be using a monitor for synchronization with respect to a high level language program written in a high level language like Java, let us say. So, it can be used very conveniently for process synchronization, very conveniently you can do that. And see, for normal critical section problem, we were talking about a common shared memory, common shared data. Some of the process was updating a common shared data, another process cannot do it at the same time. That was the critical section region you had defined. But for a monitor, we are saying that inside a monitor one process can be active at a given time. So, monitor automatically, see, when you are associating or attaching multiple processes with a monitor, it is automatically ensured that among the processes there will be synchronization. One process will be executing at a time in the monitor. Okay? Well, as I said, it also supports object oriented concept. There are some procedures or functions which are defined. Inside the procedures you can have some variables, those are the internal variables of a procedure. So, such internal variables will be local to a procedure. They can be accessed by the code which are only within that particular procedure, not from outside. But you can also define some shared variables which will be accessible across all the procedures. There can be, just going by the object oriented concept, there can be an initialization code. Whenever you create the monitor, the initialization code can automatically execute and some variable initializations and other thing can happen. So, essentially speaking, a monitor description looks like this. So, well, here I said that this is not corresponding to any particular language. This is a hypothetical notations we are using. For different programming languages, they use different notations and keywords. Let us say our convention is that we would be using the keyword monitor, saying that this is a monitor that we are defining. We specify a name, this is the name of the monitor. Now, inside a monitor there are broadly three things we are defining: shared variables, one or more procedures, and some initialization code. As I said, shared variables, whatever you are declaring here, they can be accessed by any one of the procedures, proc 1, proc 2, proc n, all of them can use the shared variables. But whatever variables you are defining inside proc 1, they can be used only from inside proc 1 only. Proc 2, proc 3, proc 4, they cannot access that. And in the monitor initialization, typically the shared variables are initialized, and anything else you need to do before the procedures are called, they are done. Now, basically when you define a monitor, you are defining some procedures. Now, the execution of these procedures are getting synchronized by processes. There can be a number of processes which are calling these procedures. Just think like this: you have a monitor, this is your monitor M. This monitor contains all these things, a set of procedures, a function calls you can call. Now, there can be many processes which are calling this monitor, calling some functions P1, P2, P3. What might so happen, the idea is like this, that one of the processes, let us say P1 was first, P1 is executing some of the procedures now. Currently, I say P1 is in the active state, but P2 and P3 had also made some function calls, but because P1 is already doing something, P2 and P3 has to wait. So, there will be some kind of waiting list again, this P2 and P3 will be waiting here. So, the concept is something like this, right, and this kind of a synchronization primitive is automatically implemented and realized by the function. Let us see pictorially. So, this is a diagram which is available in this textbook. Now, this diagram shows whatever I specified in that code. This is your monitor. Monitor can contain some shared data, it can contain some procedures, here the procedures are referred to as operations, and you can have a code to initialize the variables whenever you create the monitor. Now, whenever some processes are trying to invoke some of the procedures or functions inside the monitor, as I said, one of them will be in the active state and all others will be in the waiting queue. This monitor implementation ensures that the function execution by the processes will be automatically synchronized and mutual exclusion will be ensured. Okay. Let us look at some possible implementation of these monitors without going into too much detail. Let us see how a simple implementation of monitor can be done. Here we are using semaphores for the implementation. Here we are using two semaphores, one we are calling as mutex, one we are calling as next. This semaphore mutex, as the name implies, we shall be using it for mutual exclusion, and any semaphore which are using for mutual exclusion must be initialized to 1, that means originally unlocked. And next is another semaphore which are initializing to 0, because here we are trying to keep track of how many processes are waiting. Next is a semaphore that keeps track of that, and there is an integer variable, let us say called next count, which actually represents the number of waiting processes. So, I said that we have a monitor, there will be a number of waiting processes. So, how many processes will be waiting? That next count will be storing that number. And you recall, inside the monitor there will be several procedures. Let us consider any one procedure, let us call its name is proc. Now, the procedures are written in a special way. This is the structure of one procedure. So, for all the procedures we will be doing the same thing. So, what we are doing? Firstly, whenever a procedure is executing, no one else must be able to execute a procedure. So, the whole body of the procedure is protected by a wait in the beginning and a signal in the end. So, we are first doing a wait on mutual exclusion, which means at most one person can enter it at a time. Mutual mutex is a semaphore initialized to 1. The first person doing a wait will be able to enter, the other fellows doing a wait will have to wait. So, after wait, the body of the procedure, the instructions will come here. So, all the instructions of the procedure is there. Now, we have finished execution of the procedure, that means all the instructions have been executed. So, now what is the idea? So, I have finished execution of the procedure. Now, some other process which is waiting can now execute the procedure it wants to. Now, I should give chance, right. So, what I do now? I check whether there was any waiting process or not, if next count is greater than 0 or not. If next count is greater than 0, which means there was one process which was waiting. I signal with next. Otherwise, if there was no waiting process, I simply come out, I do a signal mutex, mutex will again become 1, I come out. And of course, I have not shown the complete solution, somewhere else there must be a wait of next. Because you see the value of next was initially 0. So, as soon as next count is greater than 0, I am signaling next, I am becoming next equal to 1. Okay. And similarly again, whenever you just come out, you will again do a wait next, next will become 0. So, the idea is that you are keeping track of the number of waiting processes, you are keeping track of whether a procedure is executing or has finished execution. While it is executing, do not allow anyone else to enter, that mutex will be protecting that. But once it is finished, you do a signal next to allow the next process to resume execution, call one of the procedures and proceed like that. Okay. So, this is the skeletal structure of the implementation. We have not shown the complete implementation, I have told already, but just the skeleton of the implementation. Now, a few other things are there. Of course, monitor ensures mutual exclusion with respect to the processes which are calling the procedures. But there are also some conditional variables that you can define with respect to a monitor, that you can define some conditional variables called condition, and with respect to a conditional variable you can invoke a function wait or a function signal similar to a semaphore wait and signal. So, when you call a dot wait, what will happen is that a process which invoke this will get blocked until someone else invokes a signal on that same variable. Similarly, a signal means one of the process which was waiting will be resumed. So, essentially this is very similar to semaphores. So, when you define a complete monitor, monitor will contain synchronization among the process executions, procedure executions. it will keep the waiting processes in a queue, just in a list. Also it can maintain such conditional variables or semaphores, because inside the procedures you can have some critical sections where the shared variables or values are accessed, you want to protect them as well. Okay. So, with this we come to the end of this lecture, where we had discussed some of the synchronization tools like semaphores and monitors. Now, in the next lecture we shall be looking at some of the classical applications of the synchronization tools, which are actually applicable to various different kinds of scenarios in real life systems. We will see that. So, we shall see how these applications can be realized, can be implemented with respect to this kind of synchronization tools which I have already discussed. And subsequently we shall be taking some case studies of Unix or Linux and show that what kind of programming support Linux or Unix has to implement a number of these things. When I write a program, when I create a process, how do I synchronize myself with respect to this critical section and other things. Thank you.